Hi, this is a continuation for power electronics tutorials, and you should have seen the first video before this one about 3 problems that we solved, covering the theory covered in the lectures. So today we are going to just discover or explore 2 more questions and how we solve them. So now let's start with problem number 4. So problem number 4 says we have a 1 kilowatt heater load that is in a food processing system, which is supplied by a converter which has an efficiency of 86% efficiency. So we have a 1 kilowatt load supplied by a converter. That converter has 86% efficiency. And that converter costs about £100. Now there is a higher efficiency converter. The efficiency is about 96.8% and is offered by you. So you have designed that converter and you want, for example, to market that. Okay, and you want to market that to the technical team for the factory, for example, and you sell it by £200. Your efficiency is higher compared with the first one, and your cost is doubled. Okay, but the team that you are offering to claims that this 10% difference between the first converter efficiency and second converter efficiency, this 10% enhancement or improvement in that efficiency needs 10 years to be paid back. Okay, so your converter, if they want to take it, the extra cost will be paid back after 10 years. Is it right or no? We will see. If the energy cost is 0.1 pound per kilowatt hour, so discuss the correctness of their claim with cost feasibility of your offer. So you want to convince them that no, the claim is not very accurate. We will see if their claim is accurate or no, and you want just to give them the right numbers for this. And this is the given energy cost they pay as a factory. So now let's take this information and translate that to some symbols and numbers. So if we say the solution here, the efficiency of the first converter equals 86%, and the cost for the first inverter equals £100. You offer them another converter that has 96.8% efficiency, and it's offered by you with a cost of £200. Now, if they want to take your offer, they have to pay £200 for that, and they say that they're gonna get the benefit after 10 years. We'll see this one. All right. So the cost of energy cost is about 0.1 pound per watt hour. All right. So this is the energy, not the power. Okay. How we think about this one? We will see first the losses that they're gonna lose if they keep the old converter, and we'll see if that's really worth a lot of money or no. And we also do the same for the new converter and compare the losses and the loss of money. Maybe we can convince them by comparing the losses and then seeing that it doesn't need 10 years to be paid back, and maybe there is another way to validate our numbers. So let's now check the losses for the first one and how much it costs for example, a year. So we know that the efficiency equals power output divided by power input. Okay, so that means the power input equals the power output divided by the efficiency. And let's say for the first one, we have the power output according to the load here. We have 1 kilowatt divided by the efficiency of the first one, which is 86. That equals 1162.8 watts. So this is the power which is input to their old converter, and that will give us just 1 kilowatt supplying our load. And remember, we want to compute the losses cost, so we have to go for pre-losses, which equals power input minus power output, and that will equal 162.8 watt. But this one is power, and you want to convert it to energy to calculate the cost. Okay, so the energy loss, which is computed by kilowatt hour. Okay, kilowatt hour is energy, not power. Okay, so be careful with this. It equals 162.8 watt, okay, times 1 hour, and that will equal 162.8 watt hour, and that will equal 0.1628 kilowatt hour. So this is the energy loss, but how much it costs we will see now. So the cost of loss equals the loss itself, which is 0.1628 kilowatt hour, times, so this one is the energy lost per hour. If we want to compute it for a year, we have to multiply 24 hours now, just to see the daily losses, and then multiply it by 365 to see the yearly losses, because the year has 365 days and each day has 24 hours, and each hour has this loss, right? So after computing this, you will come up with this number, okay, and by multiplying it by 0.1 pound per kilowatt hour, so this one is kilowatt hour, and we should multiply it by 0.1 finally cost, and that will equal 142.6 pound per year. Okay, what do you think about this price? Is it very high to make our offer feasible for them? Because our offer, which is the new converter, is £200 for the new converter, but this one is losing £142. That means about 3/4 of the price of the new converter. They will lose it in just 1 year. So in 2 years' time, they will lose more than £200. Then, in 2 years' time, okay, the losses cost about £285.2, which is more than the 200 we already offered them. So they already will lose it if they didn't get our converter. But the question is still, is our converter able to minimize these losses and make it cost feasible or no? To understand this, we have to compute the same thing for our new converter. So for the new converter, okay, the efficiency or the power losses equals power input minus power output, and the efficiency is 96.8 as we said, okay, and you will come up with every 1000 watt as output, you will spend that amount as power input. That means the power losses will equal 33.06 watt only, okay, compared with the previous one. So let's now compute that for a year. So the energy loss, 33.06 watt hour, okay, and it will equal 0.03306 kilowatt hour. So the cost of loss equals 0.033 times 24 hours times 365 days times the energy cost, which is 0.1, and that will equal about 28.9 pound. Look at the cost here and the cost there. Okay, so if they want to pay for our converter, how much they will pay. So let's now see the total cost for them equals the £200 cost of the new converter plus 28.9 pound for the first year, for example, first year losses. And if we want to compute it for just 2 years, let's add another cost for another year. okay, just to make it comparable with the first one, which we compute the losses for 2 years, okay. So that will equal 257.8 pound, okay. So compare that one now. For 2 years, this is their losses without using our converter, and this is the losses for 2 years if they bought our converter. Comparing with their claim, first, their claim is not accurate because within 2 years you can pay back your cost, and also you prevent more losses that you will pay without knowing that, okay. So it means for the payback time, it will be less than 2 years. That shows their claim they didn't consider the current losses for the current converter, okay, and they just looking at what they're gonna pay. They don't know that they will pay more if they kept the old converter. And now I think our offer is feasible. Now let's move to problem number 5. We have this figure, okay. That figure shows the voltage and current across the semiconductor device, and we have here the voltage and we have here the current. All right, so during switching transition, so there is switchings happen, maybe turn on or turn off, okay. It seems that the current was 0 here and jumped to a value. That means it conducts the current. That means it turns on. So we know now the transition is from the off condition to on condition, okay. And while is the energy, what is the energy lost during this transition? There is some transition lost, and that losses is called the switching losses, okay. So we have here 4 options. We want to choose from them which one is right, okay. Looking at the options we have, we know now the transition is from off to on, and we see there is turn off and there is turn off options, and I think you will agree with me that they are wrong. So this one is wrong and this one is wrong, okay. They are not turn off, they are turn on, okay. Let's now solve the problem and see how we are going to compute the energy during this transition. According to the waveform, we have before T1, which is this duration here, okay, the current was off, and that means there is no energy has happened. And after T2, the voltage is off and the multiplication with the current, that means the energy is 0, okay. So that the energy consumption or losses happen between these points, which is this point and that point, okay. And that is divided to 2 pieces. As you see here, we have T1 and T2, and that is the T1 and T2 separation, okay, because we have different function for voltage and current between the first duration and second duration, okay. So here the voltage is a constant, but the current here is a linear function. Here the current is constant, but the voltage is a linear function, okay. So that's why we have to separate them. Okay, now let's go for the solution. We have just 2 options to choose from, and we have energy lost in this duration, and I will call it energy 1, and we have energy lost during this duration, which is T2, and I will call it energy 2. Why? Because this makes the calculation easy. So the energy loss equals E1 plus E2. Let's now solve for E1. To calculate E1, we have to integrate over the period. What is the period? It's just T1, okay. So we can say from 0 to T1, the instantaneous power, which is the voltage times the current waveform dt or functions, and that equals integration from 0 to T1, okay. The voltage is a constant value, which is this one, okay, and the current is a linear function. And how we can get the linear function? I'm asking you here just to remind the math and how you get the line equation. If you don't know how to get the line equation, you have to make a revision, because it's not part of the module to teach you what is the line equation. But I can give you a hint, okay? So that line is like this. So we can really draw it here alone. This is the current, okay? And the value here is I, and the value here is T1. So I think this is easier now to solve the equation, and you can really get the slope. The slope is I, which is the value here, divided by the duration, which is T1, and the slope is positive, okay? So this is the slope for the equation, and to compute the equation, you have to multiply it by T, okay? And that is called now I of T as a function of T equals the slope times T, okay? So this is now the equation for the current, and this now just write it. So times I divided by T1 multiplied by T dt, okay? And we can continue from 0 to T1, and V and I, they are constant, so, and T1 as well, they are constant, so I can take them out and just VI divided by T1 and just integrate T dt, and that will equal VI divided by T1, and this will have the integration of T squared divided by 2 from 0 to T1, okay? And let's continue T1, and the integration for this one, so we have here 2, let's make it 2, okay? The integration for this one is T1 square minus 0, okay? And I think we have T1 here and T1 there, so we can really just rid off 1, and it is there, and divided by 2. So energy 1 during the first transition has this equation, okay? Let's now move to the second one by exactly the same manner. So we have energy 2 that equals integration, this time from 0 to T2, the V of T, I of T, dt, okay? And again, we have the current as constant here, okay? So we can just write I, okay? But the voltage has different function, okay? Let's now just draw it here like this, okay? And the value here is V, the value there is T2, from 0 to T2, because the duration is T2, okay? So what is the function for this line? This is the question, okay? So we want a V of T this time equals the slope. What is the slope for this one? We have 0 volt, and we have here V volt, okay? So 0 minus V, so the slope is minus, negative, divided by the duration, which is T2, multiplied by the function variable, which is T, okay? But that line is not starting from 0, it starts from V, so that's why it has like an offset or displacement, okay? So that displacement should be added as V here. So now this is the function of the voltage that we should compensate in our equation. So now we have the integration from 0 to T2, I of T, which is this one, times V of T, which is minus V, divided by T2 times T plus V capital, okay, dt. And now I think it's very easy to continue. We have here the I is constant, and we can take this voltage and that voltage out, okay, and they are constant, so I can really take them out as V, and the integration will just keep the others inside, which is 4. This is minus 1 divided by T2 T plus 1. So this is the integration that we want to conduct, okay? So IV, and the integration for the first term is minus 1 T squared divided by 2, and here is T2, plus the integration for the second one is T, and that should be from 0 to T2. Let's now, if we compensate with 0, I think all the term will be 0, so forget this one. So we have now just T2, which is IV, so it will be T2 square, but the T2 square will should take this off. So we have here just 2, and we don't forget the minus, plus T2, okay? So this is the new term now, and let's continue having, so it's like T2 can be taken as common, so we have IV T2, and this will be minus half plus 1, and that equals IV T2 divided by just 2. It's exactly the same as the first one, so we have energy number 2 as this. All right, so let's now sum them up. The total energy equals the first one plus the second one, and I think when you see it, it will be IV T1 divided by 2. They can be taken as common, so it will be just here T1 plus T2. Okay, so now let's check which one of the options have IV divided by 2 times T1 plus T2. So we have here the first one is the correct one. The third one is wrong because it doesn't have divided by 2. So this is now the energy lost in switching from off to on. And if that's very high, you are going to use that figure to calculate the average power and also to decide whether you need a heat sink or just that is very low and you don't need a heat sink for this. So all these things we are calculating now by manual, by hand, all the equations, but later on I think you can use softwares just to compute for you everything. But if you know how to compute that, it's good, because some of the researchers now, they just produce some new models for computing more accurately the switching and conduction losses. So yes, we have to know the basics before we use any other softwares. I hope you enjoyed this tutorial. I made the pacings very slow just to make it clear for every point and every step we go through. I hope you just give yourself some time to try every question before you see the solutions. That will give you opportunity to discover if you really catch up with the concept and you can really think about what are the given and what is the requested from the question, and you can go through the solution later on if you failed or you tried or you want to make sure that your answer is good. This is my advice, and that's it for this tutorial, and we'll see you in the next video. Thank you.